Most of the quantum action in cities is not about putting a quantum computer on every street corner, but about upgrading the glass that is already under our feet, the existing fiber network. Today, places like Geneva, Switzerland, are turning their ordinary telecom fiber into a living testbed for the future quantum internet. Imagine your city's internet cables quietly pulling double duty, carrying Netflix traffic and, at the same time, streams of single photons that cannot be copied or hacked without leaving a trace. That is precisely what early quantum networks are starting to do, and Switzerland has just become one of the clearest real-world examples. In this video, you will see how Geneva's new quantum network works, why it runs primarily on existing fiber, and what that means for the future of secure communication and quantum computing. Most cities already have dense fiber optic networks installed for internet, TV, and data connectivity between offices and data centers. The key takeaway from recent field trials is that you do not need to rip these out and start over to enable quantum. You can send delicate quantum signals through the same glass alongside classical traffic, using careful wavelength planning and filtering. In practice, what changes is not the cable but the gear at the ends and key junctions. You add entangled photon sources, quantum key distribution modules, ultra-sensitive detectors, and key management systems, while the buried fiber stays the same. Experiments in Berlin and elsewhere have already shown that entanglement can survive for days over commercial fiber carrying regular internet traffic on neighboring wavelengths. Now let's zoom in on Switzerland. Geneva has launched the Geneva Quantum Network, described as the country's first citywide quantum communication network. It is built directly on top of the canton's existing Oxen fiber backbone, spanning about 262 kilometers of fiber that already connects key research, government, and industry sites. The initiative brings together the University of Geneva, CERN, Rolex, the engineering school Hippia, ID Quantique, and the cantonal IT office Oxen, with IonQ contributing to quantum computing and networking. This consortium uses hundreds of kilometers of existing fiber optic infrastructure in and around Geneva to link these partners into a single, citywide quantum testbed. What is the GQN doing day to day? First, it provides a large-scale platform for quantum communication experiments, especially quantum key distribution, which uses single photons to generate encryption keys that reveal any attempt at eavesdropping. ID Quantique's QKD and quantum detection systems are deployed along the Oxen backbone, enabling secure key exchange among nodes such as Unige, CERN, and Hippia. Second, the network is designed for quantum metrology and synchronization experiments, such as distributing entangled photons and ultra-stable timing signals across the city to test precision sensing and clock sync over real fiber routes. In other words, you can think of GQN as a full-scale playground where researchers can push quantum protocols under realistic conditions, temperature changes, traffic reroutes, and all the messy details of an actual city network. Geneva is not alone in using installed fiber for quantum links. A recent multi-node QKD network demonstrated in Cyprus also operated over existing commercial underground fiber, including lines carrying live traffic on adjacent channels. By using a ring topology, bidirectional fiber use, and wavelength multiplexing, the team achieved secure key rates across multiple nodes for several days, confirming that QKD can coexist with conventional telecom use. In Berlin, a 17-day field trial maintained entanglement over city fiber, while the same conduit served regular internet to innovative city systems and other users. These tests show that you can piggyback quantum channels on the same ducts, manholes, and maintenance Windows cities already use, dramatically reducing deployment costs and accelerating pilot projects. Here is a crucial distinction for anyone hearing quantum network and thinking citywide quantum computer. The fiber is not where the quantum computing happens. It is the transport layer for fragile quantum states between specialized nodes. Right now, most nodes consist of QKD boxes, entanglement sources, and detectors, rather than full-scale quantum processors such as trapped ion or superconducting qubit systems. Geneva's GQN and similar networks are better understood as early components of a future quantum internet that will one day link remote quantum computers, sensors, and clocks. At the same time, the heavy computing hardware remains in a few secure facilities or data centers. Today's deployments focus on high-value applications like securing data center links, government communications, and critical infrastructure, where the ability to detect eavesdropping in hardware is already a meaningful upgrade. For city planners and tech strategists, the key takeaway is that quantum upgrades can primarily rely on existing assets, ducts, conduits, and fiber strands already in the ground. That means you can start with targeted pilots, connecting a government office to a data center or a hospital to a research lab without a massive civil engineering project. Before we wrap up, if you want to see more real-world quantum stories like Geneva's citywide quantum network, built on existing fiber and already securing critical links between universities, government, and industry, make sure you hit subscribe and turn on notifications. Drop a comment telling which part of your city you would upgrade first with quantum secure fiber, and share this video with a friend who still thinks quantum is just theory, so they can see how fast it is becoming real infrastructure. As more pilots like Geneva, Berlin, and Cyprus succeed, the roadmap points toward interconnected metro quantum networks, then regional links via quantum repeaters and satellites, and eventually a global quantum internet that coexists with today's classical web. When that happens, the cities that are experimenting now on their existing fiber will be the first to plug real quantum computers and sensors into a secure, high-value network layer.